Welcome to the fourth dimension, a place where the familiar rules of space and time begin to dissolve. Here, length, width, and height are only the surface of reality, and beyond them lies a hidden structure that shapes the universe in ways we can barely imagine. Before we set out, I'd love to know, where are you listening from, and what time is it there? It's always fascinating to see how far and wide this curious little journey reaches. Now, let's step beyond the edges of perception and explore the unseen architecture of the universe together. Imagine this: you're standing in your kitchen, holding a coffee mug. You can see it from the front, the side, the top. You can walk around it, tilt it, spin it in your hand. You don't even think about it, because you live in a world where your brain and senses are wired to perceive three spatial dimensions: height, width, and depth. It's so natural you don't even realize you're doing it. Now, shrink yourself down, way down. You're an ant crawling across the countertop. Your world is the flat surface beneath your feet. You can go forward, backward, left, and right, but up and down aren't really part of your mental map. Sure, you can climb, but you don't conceptualize depth the way we do. You're essentially living in a two-dimensional mindset inside a three-dimensional world. And here's the kicker: that's not because the third dimension doesn't exist for the ant. It's because its sensory and cognitive systems aren't built to process it. It's like trying to explain colour to someone who's been blind from birth. The reality is there. It's just outside the range of their perception. We humans love to think we're the ultimate perceivers, the top of the sensory food chain. But here's the uncomfortable truth: we're just as limited as that ant. Our eyes only pick up a tiny slice of the electromagnetic spectrum, what we call visible light. Our ears are tuned to a narrow band of sound frequencies. There's an entire ocean of reality: radio waves, gamma rays, infrasound, ultraviolet light. That's invisible and inaudible to us. And yet, because we can't sense it directly, we tend to act like it's not there. That's the trap of perception. It tricks you into thinking your sensory window is the whole picture. Back in 1884, a writer named Edwin Abbott created a little book called Flatland. It's about a world that exists entirely in two dimensions. No up or down, just length and width. The inhabitants are flat shapes: squares, triangles, circles, sliding around on a plane. Now imagine a three-dimensional sphere passing through Flatland. To the Flatlanders, it wouldn't look like a sphere at all. First, they'd see a tiny dot appear out of nowhere. Then it would grow into a circle, get bigger, then smaller, and finally vanish. They'd have no idea they were seeing slices of a higher dimensional object. That's us! If a higher dimensional being passed through our world, we might only see fragments of it, slices in time and space, without ever realizing the full shape. Modern physics, especially theories like string theory and M-theory, suggest there could be 10, maybe 11 dimensions woven into the fabric of the universe. We perceive 3 of them, plus time as a 4th. The rest could be curled up, hidden, or simply beyond our sensory reach. Think about that. We might be like fish in a pond, completely unaware of the air above the surface. The surface of our reality might just be one layer in a much bigger, stranger structure. And this isn't just a fun mental game. It's a reminder that our perception is not reality. It's a filtered, edited version of reality. History has shown us that every time we've expanded our perception, whether it was Galileo pointing a telescope at the heavens or scientists building particle accelerators, we've discovered worlds we never knew existed. It also means that the universe could be teeming with phenomena we can't even imagine yet. Not because they are impossible, but because we're not equipped to detect them. And here's the thing about humans: we hate being limited. We build tools to extend our senses, telescopes to see farther, microscopes to see even smaller, radios to hear frequencies our ears can't, infrared cameras to see heat. Every one of those inventions is a rebellion against the prison of our biology. And every time we break out, we find something that changes the way we see ourselves and our place in the cosmos. So here's the question that should be buzzing in your head right now. If we're missing dimensions, if we're blind to most of the universe's signals, what else is out there? What's hiding in plain sight, just beyond the reach of our senses? Because if history is any guide, the moment we find a way to peek beyond our sensory cage, the universe is going to look nothing like we thought. Picture this. You're standing in a dark room. You've only ever known this room. You've memorized every corner, every shadow. Then one day, someone hands you a flashlight. You flick it on and realize the room has a door. And behind that door, an entire world you never knew existed. That's what expanding perception feels like. And that's where our journey begins. We start here because everything else we're going to talk about, from the invisible waves all around us, to the bending of spacetime, to the strange rules of quantum mechanics, all of it is built on this one truth. What you perceive is not all there is. Once you accept that, you're ready to start seeing the universe for what it really is, not just the slice your senses feed you. If our senses can't even grasp all the dimensions around us, what else are we missing? Well, it turns out we're blind to most of the universe's signals too, and the proof is hiding in plain sight, in the light hitting your eyes right now. The colours you see are just one tiny station on the universe's broadcast. And the moment you realise how much you're not seeing, that's when the real story begins. Picture this. It's a perfect summer afternoon. The sky is a deep, endless blue, the grass is green, the sun is warm on your face, and you're thinking, yeah, I'm seeing the world exactly as it is. Wrong. What you're seeing is a lie, or at least a heavily edited highlight reel. Because here's the truth. Your eyes are tuned to one tiny razor-thin slice of reality. A narrow band of wavelengths we call visible light. That's it. That's your whole window. The universe is constantly broadcasting on a massive range of frequencies, the electromagnetic spectrum, and visible light is just a sliver in the middle. Imagine the spectrum as a giant piano keyboard stretching from here to the moon. The part your eyes can detect is just one single key. On one end of the keyboard are radio waves, gentle giants with wavelengths the size of buildings, carrying your favourite songs, your GPS signals, your late-night talk shows. On the other end are gamma rays, tiny high-energy bullets born in the hearts of exploding stars, powerful enough to shred DNA. And in between are microwaves, the same kind that heat your leftover pizza, infrared, the heat your skin feels from the sun or a campfire. Ultraviolet, the stuff that gives you a tan or a sunburn. And X-rays, the ones that let doctors peek inside your bones. All of it is happening around you right now. You're swimming in it, but without technology you'd never know it was there. It's like living in a mansion with 1,000 rooms, but you've only ever been allowed to stand in the hallway. You think you know the place, but you've barely scratched the surface. Your eyes are the hallway. The rest of the mansion, that's the electromagnetic spectrum. And here's the kicker. Humans aren't even the best at this. Every creature on Earth has its own unique window into reality. Bees can see ultraviolet patterns on flowers that guide them like runway lights to nectar. Snakes can sense infrared heat signatures, letting them hunt in total darkness. Bats navigate with ultrasonic sound waves, painting the world in echoes. The mantis shrimp can detect polarized light and see colors far beyond our comprehension. We humans, we're basically walking around with blinders on, convinced we've got the full picture. Now here's where it gets wild. If you could suddenly see the full electromagnetic spectrum, the world would look alien. The night sky would blaze with radio galaxies. Your living room would glow with Wi-Fi signals. Every warm body, human, animal, machine, would shine like a beacon in infrared. Gamma rays from distant supernovae would streak across the heavens like cosmic lightning. It would be overwhelming, beautiful, terrifying. The only reason we even know about this hidden world is because we've built machines to detect it. Radio telescopes let us hear the whispers of distant galaxies. Infrared cameras reveal heat. X-ray observatories peer into the violent hearts of black holes. Every time we've extended our senses with technology, we've discovered something that rewrote our understanding of the universe. Think about the cosmic microwave background, the faint afterglow of the Big Bang. It's not visible to the naked eye. But when scientists built instruments to detect microwaves, they found this ancient light stretched across the sky, carrying the story of the universe's birth. Or consider gamma ray bursts, the most energetic explosions in the cosmos. Without gamma ray detectors, we wouldn't even know they existed. Now we know they can release more energy in a few seconds than our sun will in its entire lifetime. Here's the big takeaway. Your perception is not reality. It's a filter. A curated feed. Evolution didn't give you eyes to see the truth. It gave you eyes to see just enough to survive. But survival and understanding are two different games, and if we want to understand the universe, we have to break out of the sensory prison evolution built for us. Do you see the pattern forming? In the first part of our journey, we saw that our perception of dimensions is limited. Now, we see that even within the dimensions we can perceive, we're missing most of the action. The universe is broadcasting on every channel, all the time. We're just tuned to one station. And here's the philosophical gut punch. If we're missing this much in something as basic as light, what else are we missing in the deeper structure of reality? Because light isn't just a way to see, it's the messenger of the universe. It carries information across billions of light years, and the way it moves, bends and stretches tells us about the shape of spacetime itself. Which means, if we really want to understand the universe, we have to understand the stage light travels on. That stage, the invisible arena where light, planets and galaxies all move, isn't flat. It isn't rigid. It's alive. It bends, curves and stretches under the weight of stars and black holes. And that's where we meet the man who didn't just peek beyond the sensory cage, he tore it open and showed us the architecture of reality itself. We've been talking about the signals, the light, the waves, the messengers of the cosmos, but what about the stage they travel on? What if space and time aren't just empty backdrops but living, flexible fabric? And what if gravity isn't a force at all, but the bending of that fabric under the weight of the universe? That's the revolution Einstein unleashed, and it's where our journey goes next. Let's rewind to a time when the universe seemed simple. For over 2 centuries we'd been living in Sir Isaac Newton's world. Gravity was an invisible force pulling objects toward each other. The Earth pulls the moon, the sun pulls the Earth, and when you drop your phone it falls because the Earth is pulling it down. Newton's equations worked beautifully. They could predict the motion of planets, the fall of an apple, the arc of a cannonball. Engineers built bridges. Astronomers charted the heavens, sailors navigated the seas, all thanks to Newton's math. But here's the thing, Newton never explained how gravity actually worked. He could describe it, but he couldn't tell you what was causing that invisible pull. He even admitted it was inconceivable that masses could act on each other without something in between. He didn't have the tools to go further, and for 200 years nobody really questioned it. Why would they? It worked. By the late 1800s, though, tiny cracks began to appear in Newton's perfect picture. Astronomers noticed that Mercury's orbit didn't quite match Newton's predictions. It wobbled just a little, in a way that couldn't be explained by the pull of other planets. It was a small discrepancy, but in science, small discrepancies are often the universe whispering you're missing something. Enter Albert Einstein, not yet a famous professor, but a 26-year-old working in a Swiss patent office, reviewing inventions and running mental experiments by night. In 1905, he dropped his first bombshell, the special theory of relativity. It showed that space and time aren't separate. They're fused into a single four-dimensional fabric called spacetime. And in this fabric, the speed of light is the ultimate speed limit. But special relativity didn't touch gravity. That was the next mountain to climb. Einstein's breakthrough came from what he called the happiest thought of my life. Imagine you're in a sealed elevator, floating in deep space far from any planets or stars. Suddenly the elevator starts accelerating upward. You feel your feet pressed to the floor. Now imagine the same elevator sitting on Earth. You feel your feet pressed to the floor again, this time because of gravity. Einstein realized there's no experiment you could do inside that elevator to tell the difference between acceleration and gravity. They are the same thing. This is the equivalence principle, and it became the cornerstone of his new theory. Here's where Einstein flipped the script. He proposed that gravity isn't a force pulling objects together, it's the warping of space-time itself. Picture space-time as a giant invisible trampoline stretched tight. Place a bowling ball representing the sun in the middle, and the trampoline dips. Now roll a marble representing the Earth across the surface. The marble curves around the dip, not because the bowling ball is pulling it, but because the surface itself is curved. In Einstein's universe, mass tells space-time how to curve, and curved space-time tells mass how to move. And it's not just space that curves, time does too. The stronger the gravity, the slower time runs. This isn't poetic, it's measurable. Astronauts on the International Space Station age a tiny bit slower than we do on Earth. GPS satellites have to account for both their speed and the weaker gravity up there, or your phone's location would drift by miles each day. Einstein spent nearly a decade wrestling with the math to describe this curved space-time. He had to learn advanced geometry, Riemannian geometry, that most physicists of his time didn't touch. In 1915, he finally unveiled the general theory of relativity. It was a set of equations so elegant and so strange that even other scientists didn't fully grasp it at first. But it made bold predictions that could be tested. One of those predictions was that light would bend when passing near a massive object because space-time is curved there. Newton's theory predicted some bending, but Einstein's predicted twice as much. In 1919, during a total solar eclipse, British astronomer Sir Arthur Eddington led an expedition to photograph stars near the sun's edge. The results matched Einstein's prediction perfectly. Overnight, Einstein became a global celebrity. Newspapers declared, "Revolution in science. Newtonian ideas overthrown." Einstein's theory didn't just explain Mercury's orbit or the bending of starlight. It redefined our understanding of reality. Space and time weren't static backdrops. They were dynamic, flexible, and responsive to matter and energy. It also opened the door to phenomena Newton's theory couldn't even imagine. Black holes, regions where space-time curves so much that nothing, not even light, can escape. Gravitational waves, ripples in space-time caused by massive objects in motion, confirmed a century later by LIGO detectors, and time dilation, the idea that time itself can run at different rates depending on gravity and speed. Here's a mind-bender. Right now, you're not being pulled toward Earth. You're moving along the straightest possible path in curved space-time, a path that happens to intersect with the ground. If Earth suddenly vanished, you wouldn't feel a release from a pull. You'd just keep moving in a straight line through flat space-time. And time? It's running a hair slower for you at sea level than for someone on a mountaintop, because you're deeper in Earth's gravitational well. The difference is tiny, but it's real, and it's why GPS satellites need relativistic corrections to work. If space-time can bend, twist and stretch, could it also fold? That's the tantalizing idea behind wormholes. Hypothetical tunnels connecting distant points in space-time. In theory, they could allow instant travel across the universe. We'll dive into wormholes later, but here's the teaser. They're not just science fiction, they're legitimate solutions to Einstein's equations, though whether they can exist in reality is still an open question. Think about the pattern so far. First, we learned our perception of dimensions is limited. Then we saw that our senses only catch a sliver of the electromagnetic spectrum. Now, Einstein shows us that even the force we thought we understood best isn't a force at all. It's geometry. Each step peels back another layer of the illusion we call reality. And each step hints that the universe is far stranger, and far more interconnected than our everyday experience suggests. Einstein's general relativity has passed every experimental test thrown at it for over a century. From the bending of light to the detection of gravitational waves, the evidence keeps piling up. But here's the twist. We know it's not the final word. General relativity doesn't play nice silly with quantum mechanics, the theory that governs the subatomic world. Somewhere out there, a deeper theory is waiting, one that unites the smooth curves of space-time with the jittery probabilities of quantum physics. And when we find it, it might make Einstein's revolution look like just the opening act. Why should you care about curved space-time? Because it's a reminder that the universe is not what it seems. The ground beneath your feet, the flow of time on your watch, the path of light from a distant stars. All of it is shaped by an invisible geometry you can't see, but that shapes every moment of your life. It's also a reminder that the biggest breakthroughs often come from questioning the most obvious things. Gravity was settled science for 200 years, until someone dared to ask, what if we've got it wrong? Einstein gave us the blueprint for the universe's architecture, a living, bending fabric of space and time. But to explore it, to measure it, to test it, we needed power, real tangible energy. And that story doesn't start with a supercomputer or a rocket. It starts in a modest London lab. Let's set the scene. It's the early 1800s. The Industrial Revolution is roaring. Steam engines are the kings of power. Coal is the lifeblood of industry. And electricity is still more of a parlor trick than a practical tool. Scientists know about static electricity. Rub a piece of amber and it attracts dust. They know about lightning. Ben Franklin had flown his famous kite decades earlier. And they know about magnetism. Compasses have been guiding sailors for centuries. But electricity and magnetism? They're like two strangers at the same party. People suspect they might be related, but no one has made the introduction yet. In 1820, Danish physicist Hans Christian Ørsted makes a startling discovery. An electric current can deflect a compass needle. Electricity can create magnetism. That's huge. But science is a two-way street. If electricity can make magnetism, can magnetism make electricity? That's the million-dollar question, and it's Michael Faraday who's going to answer it. Faraday isn't born into privilege. He's the son of a blacksmith, grows up in poverty, and has only the barest formal schooling. He works as a bookbinder's apprentice, and it's there, binding volumes of scientific lectures, that he falls in love with science. He devours every page he can get his hands on. Eventually, he attends lectures by the great chemist Humphrey Davy, takes meticulous notes, and boldly sends them to Davy himself. Impressed, Davy hires him as a lab assistant. Faraday's rise isn't about pedigree. It's about relentless curiosity, hands-on experimentation, and a refusal to accept "we don't know" as an answer. It's 1831. Faraday is in his lab, surrounded by coils of wire, iron rings, and magnets. He's been chasing the idea that maybe, just maybe, magnetism could be used to generate electricity. He takes a thick iron ring and winds two separate coils of insulated wire around opposite sides of it. One coil is connected to a battery, the other is connected to a galvanometer, a device that detects electric current. When he connects the battery to the first coil, nothing happens in the second coil. No steady current. But here's the twist. When he connects or disconnects the battery, when the magnetic field is changing, the galvanometer needle jumps. Faraday realizes something profound. It's not the presence of a magnetic field that creates electricity. It's the change in the magnetic field. Move a magnet through a coil of wire, or move the coil around the magnet, and you get a current. This is electromagnetic induction, the principle that moving magnetic fields can generate electric currents. With that, Faraday has unlocked the mechanism for turning motion into electricity. It's the foundation of every electric generator in the world today. Power plants are just giant turbines spinning magnets inside coils. Wind turbines work on the same principle. Wind spins the blades spin the magnets, and the magnets induce current. Your car's alternator? Same idea. Without Faraday's discovery, we'd still be living in a world lit by candles and powered by steam. Faraday doesn't stop at the lab bench. He builds the first primitive electric generator, a copper disc rotating between the poles of a magnet, producing a continuous current. It's not powerful, but it proves the concept. Mechanical energy can be converted into electrical energy. That's the moment the door to the electrical age swings wide open. What makes Faraday's story so inspiring is that he isn't chasing fame or fortune. He's chasing understanding. He once said, "Nothing is too wonderful to be true if it be consistent with the laws of nature." He believes nature's laws are there to be discovered, and that anyone, no matter their background, can uncover them with patience, observation, and creativity. Faraday's work doesn't just lead to generators. It lays the groundwork for James Clerk Maxwell's equations, which unify electricity, magnetism, and light into a single theory. It gives birth to the entire field of electrical engineering. It makes the modern power grid possible. Every time you flip a light switch, charge your phone, or watch a movie on a laptop, you're cashing in on Faraday's breakthrough. He's also a master communicator. He gives public lectures at the Royal Institution, making science accessible to ordinary people. His Christmas lectures for young audiences become legendary, a tradition that continues to this day. He understands something we've been talking about since the very beginning of our journey. Science isn't just about facts and formulas. It's about storytelling. It's about making people feel the wonder of discovery. Up to now, we've been talking about perception limits, hidden dimensions and the geometry of space-time, concepts that can feel abstract. Faraday's story is the perfect reminder that sometimes the universe's deepest secrets reveal themselves in the most tangible, practical ways. Electromagnetic induction isn't just a theory, it's a tool. It's the bridge between invisible forces and real-world power, and it's a perfect example of how understanding the fundamental laws of nature can change the course of human history. Think about it. Without Faraday, there's no large-scale electricity. Without electricity, there's no modern physics experiments, no radio telescopes, no particle accelerators. Without those, our understanding of space-time, wormholes, and quantum mechanics would be stuck in the Dark Ages. Faraday didn't just give us a way to light our homes, he gave us the tools to light up the universe. And here's where the continuity kicks in. Faraday's discovery is the beating heart of our technological civilization. It's the reason we can build the massive particle colliders that probe the quantum world. It's the reason we can power the supercomputers that model black holes and simulate wormholes. It's the reason we can even dream about the kind of advanced civilizations, like the They in Interstellar, who might manipulate space-time itself. Faraday's induction coil is, in a very real sense, the ancestor of every piece of tech we've talked about so far, and every piece we'll talk about next. So picture it. A modest lab in 1831, a man in a worn waistcoat, hands stained with chemicals, winding copper wire around an iron ring. No fanfare, no headlines. Just a quiet moment of connection between human curiosity and the laws of nature. That moment sends ripples through time, powering the world we live in and the worlds we've yet to explore. Faraday's spark lit the electrical age, giving us the tools to measure and test the universe's deepest theories. Decades later, those tools would help prove one of Einstein's boldest predictions during a fleeting moment when the moon's shadow turned day into night, and the bending of starlight revealed the very curvature of space-time itself. Let's rewind to 1915. Einstein has just unveiled his general theory of relativity, a theory so radical it doesn't just tweak Newton's laws, it rewrites the very nature of gravity. In Einstein's universe, gravity isn't a force pulling on objects. It's the curvature of space-time itself, bent by mass and energy. It's a beautiful idea, elegant, mind-bending, but in science, beauty isn't enough. You need proof. Einstein's theory made a prediction so bold, so specific, that it could be tested. Light, he said, would bend when it passed near a massive object. Newton's theory also predicted bending, but only a little, because in Newton's view, light particles would be pulled by gravity like anything else. Einstein's equations, though, said the bending should be twice as much. That's the kind of difference you can measure if you can find the right conditions, and those conditions would come during a total solar eclipse. Normally, the sun's glare drowns out the stars near it. But during a total eclipse, the moon blocks the sun's light, revealing the background stars. If Einstein was right, the positions of those stems would appear slightly shifted, not because the stars had moved, but because their light had been bent by the sun's warped space-time. Arthur Eddington, a British astronomer and mathematician, was one of the few people in the world who truly understood Einstein's new theory. He also happened to be a Quaker and a pacifist, which mattered because this was the middle of World War I. Britain and Germany were enemies, and Einstein was German. But Eddington saw something bigger than politics. He saw a chance to test an idea that could change our understanding of the universe forever, and he was willing to stake his reputation on it. The next total solar eclipse would occur on May the 29th, 1919, and it would be a long one, over 6 minutes of totality in some places. That's an eternity in eclipse terms, and it gave astronomers a precious window to take photographs of the stars near the sun. Eddington organised 2 expeditions, one to the island of Príncipe, off the coast of West Africa, and another to Sobral in northern Brazil. The plan was simple in theory, but brutal in execution. Photograph the star field during the eclipse, then compare it to photographs of the same stars taken at night when the sun was nowhere near them. Any shift in position would reveal how much the light had been bent. This was 1919. There were no digital cameras, no instant previews, no let's check the footage. They were using heavy, fragile photographic plates, lugged across oceans through tropical heat and humidity. And remember, this was just months after the end of World War I. Supplies were scarce, travel was dangerous, the expeditions were expensive and politically sensitive. If they failed, it wouldn't just be a scientific disappointment, it could be a personal and national embarrassment. On May the 29th, 1919, the teams were in position. In Príncipe, Eddington's crew faced cloudy skies and tropical rain. In Sobral, the Brazilian team had clear skies, but their main telescope overheated in the sun before totality, warping the images. It was chaos. Every second counted. The astronomers had to swap photographic plates in near darkness, time exposures perfectly, and pray the weather held. And then the moon slid in front of the sun. Day turned to night. The corona, the sun's ghostly outer atmosphere, flared into view, and there, faint but visible, were the stars of the Hyades cluster, right next to the sun's edge. Click, click, click. Plate after plate was exposed. 6 minutes later, the sun's blinding light returned, and it was over. Back in England, the plates were developed and measured. This was painstaking work, measuring the positions of stars to fractions of a millimetre, accounting for distortions in the plates, the telescopes, even the atmosphere. And then came the moment of truth. The Sobral team's backup telescope, a smaller, less affected instrument, gave the clearest results. The measured deflection of starlight was about 1.75 arcseconds. Einstein's prediction, 1.75 arcseconds. Newton's prediction, about 0.87 arcseconds. The data matched Einstein perfectly. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The headline in the Times the next day read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Overnight, Einstein went from an obscure theoretical physicist to a global celebrity. His wild, abstract equations had been vindicated by the bending of starlight on a tiny island under a darkened sky. The 1919 eclipse wasn't just about proving theory. It was about proving that the universe is stranger, more flexible, and more interconnected than we thought. It showed that space and time aren't rigid backdrops. They're dynamic, malleable, and shaped by the matter and energy within them. It confirmed that light, the fastest thing in the universe, could be bent, not by a force pulling on it, but by the geometry of space-time itself. And it was a triumph of international science in a world still reeling from war. A British-led team had confirmed the work of a German scientist, bridging a divide that politics had deepened. Eddington later wrote about the moment he saw the results. He said it wasn't just about numbers, it was about a feeling. The feeling that we had taken a step closer to understanding the mind of the universe. And Einstein, when told the results matched his prediction exactly, he reportedly said, "I knew it. When asked what he would have done if the results had disagreed, he smiled and said, "Then I would have felt sorry for the good Lord." The theory is correct. The 1919 eclipse became one of the most famous experiments in the history of science. It cemented general relativity as the new foundation for our understanding of gravity. It also set the stage for everything that came after: the discovery of black holes, the detection of gravitational waves, and the realization that the universe is expanding. Without that eclipse, Einstein's theory might have remained a beautiful idea without proof, and the 20th century's physics revolution might have taken a very different path. Think about the arc we've been on. We started with the limits of perception. We saw that even light, our main messenger from the cosmos, is just a tiny slice of reality. We learned that gravity is the curvature of space-time, and now we've seen that curvature proven, not in a lab, but in the sky itself. The bending of starlight in 1919 wasn't just a test of physics. It was a reminder that the universe will reveal its secrets, but only if we're willing to go to the ends of the earth to look. The eclipse of 1919 showed us that the universe bends light itself, that space-time curves under the weight of stars. But what happens when we stop looking at the vastness of the cosmos and zoom all the way down to the tiniest building blocks of reality? There we find something even stranger. A world where the very act of looking changes what we see. Welcome to the quantum realm, where observation isn't just passive, it's part of the story. Let's start with a confession. The quantum world doesn't care about your intuition. It doesn't care about your common sense, your gut feelings, or the way you think reality should behave. Down here, particles can be in two places at once. They can tunnel through barriers. They can talk to each other instantly across vast distances. And here's the kicker. The very act of looking at them changes what they do. This is the quantum observer effect, and it's one of the most mind-bending ideas in all of science. The story begins in the early 1800s with Thomas Young's famous double-slit experiment. At the time, scientists were debating whether light was made of particles or waves. Young set up a simple test. Shine light at a barrier with two narrow slits, and watch what pattern appears on a screen behind it. If light were particles, you'd expect two bright bands, one behind each slit. But that's not what happened. Instead, Young saw an interference pattern, a series of light and dark bands like ripples overlapping in a pond. That's a wave pattern. Light, it seemed, was a wave. Case closed, right? Not so fast. Fast forward a century. Scientists discover that light also behaves like particles, little packets of energy called photons. And not just light, electrons, atoms, even molecules can show wave-like behavior. So they redo the double-slit experiment, but this time they fire particles, say electrons one at a time. You'd expect them to pile up in two neat bands, but no. Over time they still form an interference pattern, as if each electron is somehow going through both slits at once and interfering with itself. That's already strange, but it gets stranger. What if we try to catch the electron in the act? Place a detector at the slits to see which one it goes through. The moment you do that, the moment you observe the electron's path, the interference pattern disappears. The electrons start behaving like regular particles, going through one slit or the other. It's as if the electron knows it's being watched and changes its behavior. This is the heart of the quantum observer effect. Particles at the quantum scale don't have definite properties until they're measured. Before you look, they exist in a superposition, a blend of all possible states. When you measure, that superposition collapses into a single outcome. In the double-slit experiment, before measurement, the electron is a wave of probabilities going through both slits. When you measure, it chooses a slit and behaves like a particle. And it's not just about light and electrons. At the quantum level, everything, atoms, molecules, even small clusters of molecules, can show this wave-particle duality. The bigger the object of all, the harder it is to see, but the principle holds. And here's the mind bender. The line between quantum and classical isn't sharp. In theory, the same rules apply to you, me, and the moon. It's just that for large objects, the effects are drowned out by constant interactions with the environment. When we say observation in quantum mechanics, we don't mean a conscious human peering through a microscope. Observation means any interaction that extracts information from the system. A photon bouncing off an electron, a detector registering a signal, anything that forces the system to choose a state. But that hasn't stopped people, including some physicists, from wondering if consciousness plays a role. That's where the famous Schrödinger's cat thought experiment comes in. Erwin Schrödinger imagined a cat in a sealed box with a radioactive atom, a Geiger counter and a vial of poison. If the atom decays, the Geiger counter triggers, breaking the vial and killing the cat. If it doesn't decay, the cat lives. According to quantum mechanics, until you open the box and observe the system, the atom is in a superposition of decayed and not decayed, and the cat is in a superposition of alive and dead. Schrödinger's point wasn't that the cat is literally both alive and dead in some mystical way, but to show how absurd quantum rules seem when applied to everyday objects. And yet the math says that at the quantum level, superposition is pretty real. Einstein hated this. He famously said, "God does not play dice with the universe." He believed there must be hidden variables, unknown factors that determine the outcome before we measure. Niels Bohr, one of the founders of quantum mechanics, disagreed. He argued that quantum mechanics is complete, that reality at the smallest scales is fundamentally probabilistic. Decades of experiments have sided with the Bohr. The randomness is real. The universe, at its core, plays dice. If the observer effect is strange, entanglement is stranger. When two particles become entangled, their properties are linked, no matter how far apart they are. Measure one, and you instantly know the state of the other, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance and thought it was impossible, but experiments have confirmed it again and again. Entanglement doesn't let you send information faster than light, but it does show that quantum reality is deeply interconnected in ways that defy classical logic. And this isn't just a curiosity. The observer effect is the foundation of technologies that run our world. Semiconductors, the chips in your phone and computer, rely on quantum mechanics. Lasers, used in everything from barcode scanners to eye surgery, are quantum devices. Quantum cryptography uses the observer effect to detect eavesdropping. Quantum computers harness superposition and entanglement to solve problems classical computers can't touch. Without understanding the observer effect, none of this would exist. It also forces us to ask uncomfortable questions. Is reality out there when we're not looking, or does it only crystallize when measured? Are we participants in the universe's unfolding, not just passive spectators? If the act of measurement changes reality, what does that say about the nature of truth? Physicist John Wheeler once said, "We are participators in bringing about something of the universe in the distant past." In other words, maybe the universe isn't a fixed movie we're watching, but maybe we're part of the script writing process. Here's where our journey's continuity kicks in. The 1919 eclipse showed us that space-time bends under gravity's hand. The quantum observer effect shows us that at the smallest scales, reality itself bends under the act of measurement. It's as if the universe has two faces. On the cosmic scale, It's a smooth, curved fabric shaped by mass and energy. On the quantum scale, it's a jittery, probabilistic haze that solidifies only when we interact with it. The great challenge of modern physics is to unite these two faces into a single theory, a quantum theory of gravity. One of my favourite stories is about Richard Feynman, the Nobel Prize-winning physicist. He once said, "I think I can safely say that nobody understands quantum mechanics." And he meant it. Even the people who use it every day to design electronics and predict experiments don't claim to truly understand it in the intuitive sense. And yet it works. The equations predict experimental results with mind-blowing accuracy, sometimes to 14 decimal places. That's the paradox. Quantum mechanics is the most successful theory in the history of science, and also the most baffling. The speed of light. Just saying it feels like you're invoking some kind of cosmic law, and in a way you are. It's not just a number, though that number is staggering, 299,792,458 meters per second, or about 186,000 miles every single second. In the time it takes you to blink, light has already circled the Earth more than 7 times. It's the fastest thing in the universe, and according to Einstein's theory of relativity, it's not just fast, it's the ultimate speed limit. Nothing with no mass, no signal, no particle, no whisper of information can outrun it. This isn't a maybe rule, this is the bedrock of reality. What makes it so special is that it's not just about light itself. That speed in c in the equations is woven into the very fabric of space-time. It's the constant that links energy and mass in Einstein's famous E equals mc squared. It's the number that shows up in every relativistic calculation, whether you're talking about photons, gravitational waves, or the fastest possible cause and effect chain in the cosmos. And here's where things start to get strange. The closer you get to that limit, the more the universe begins to warp around you in ways that defy everyday logic. Imagine you're in a spaceship, slowly pushing the throttle forward. At first, nothing feels unusual, but as your speed climbs toward a significant fraction of light speed, time itself begins to stretch. Your onboard clock ticks normally for you, but when you look out at the rest of the universe, everything else seems to be moving in slow motion. From the perspective of someone watching you from Earth, it's the opposite. Your clock is running slow, your ship is shorter in the direction of travel, and your mass is climbing toward infinity. This isn't science fiction, we've measured it. Muons created high in the atmosphere live longer when they're moving near light speed. GPS satellites have to correct for both gravitational and velocity-based time dilation just to keep your phone's navigation from drifting miles off course. The faster you go, the more extreme these effects become. Distances in front of you seem to contract, as if the universe is being squashed in the direction you're travelling. The stars ahead shift toward the blue end of the spectrum, while the ones behind you slide toward red. And the energy cost of pushing faster skyrockets. At 99% of light speed, you're already burning through absurd amounts of energy. At 99.9999%, you're pouring in more energy than entire civilizations could produce. And still you can't quite get there. That's the cruel truth. For anything with mass, light speed is unreachable. Photons, though, are born there. They have no rest mass, so they don't have to accelerate to light speed, they simply exist at it. And here's the real mindbender. From a photon's point of view, if such a thing can even be said, time doesn't pass. The moment a photon leaves the surface of the sun and the moment it strikes your eye are the same moment for the photon. For us, that journey takes about 8 minutes. For the photon, there is no journey, no time. no distance. The start and end points are collapsed into one. In a sense, for light, the entire universe is a single instant. Past, present, and future are all the same now. That's why the speed of light is so much more than a number. It's the thread that stitches space and time together into spacetime. It's the reason causality, the idea that causes come before effects, holds up. If you could somehow go faster than light, you could, in theory, send information into the past. You could break the chain of cause and effect. You could create paradoxes. And the universe seems to have built-in safeguards to prevent that from happening. Relativity doesn't just discourage faster than light travel. It makes it physically impossible without rewriting the rules of reality itself. Of course, that hasn't stopped us from dreaming about ways to cheat. Wormholes, warp drives, Alcubierre bubbles, all ideas that try to sidestep the limit by bending space-time instead of moving through it faster than light. In theory, you could contract the space in front of you and expand the space behind you, riding a wave of warped space-time to your destination. Locally, you'd never break the speed limit. Globally, you'd get there faster than light could in normal space. But in practice, these ideas require exotic matter and negative energy densities we've never seen in usable amounts. They're tantalizing, but for now, they live in the realm of theory and science fiction. Still, the implications of the speed of light are profound. It means that the universe is vast, not just in size, but in time. The light from the Andromeda galaxy that hits your eyes tonight left there over 2 million years ago. You're seeing it as it was when early humans were just learning to use tools. Look farther, and you're looking deeper into the past. The farther away something is, the older the light you're seeing. In a very real sense, our telescopes are time machines, but only into the past. And here's where it gets even more fascinating. While you can't go faster than light, you can use relativity to travel into the future. If you could accelerate to near light speed and then come back, you'd find that more time had passed for everyone else than for you. This isn't a trick. It's been confirmed with high-speed particles and even with precise atomic clocks flown on jets. Push it far enough and you could leap decades or centuries into the future in what felt like days to you. But going backward, that's where the trouble starts. The equations of relativity don't forbid certain kinds of closed time-like curves, paths through space, time that loop back on themselves. But creating them would require conditions so extreme and so unstable that they might be impossible. And even if you could, you'd run headlong into the paradoxes that have haunted time travel stories for centuries. Change the past and you might erase the conditions that allowed you to travel back in the first place. The speed of light, then, is both a gateway and a guardrail. It's the reason the universe has the structure it does. It's the reason we can talk about before and after with confidence. And it's the reason that while the stars may call to us, they remain heartbreakingly far away. It's a limit that shapes our dreams as much as our reality. And yet limits have a way of inspiring us. Every time humanity has hit a wall, we've found a way to climb it, go around it, or turn it into a doorway. Maybe one day we'll find a way to bend space-time to our will, to step through a wormhole or ride a warp bubble to another star. Maybe we'll discover that the speed of light isn't the end of the road, but just the edge of the map. Until then, it remains the ultimate challenge. The line in the cosmic sand that dares us to try. Which brings us to the final, most tantalizing question of all. If we can use relativity to leap into the future, and if the universe's geometry sometimes hints at loops in time, could we ever truly travel through time itself? Could we visit the past, meet our ancestors, witness the birth of the stars? Or would the universe fight us every step of the way, protecting its timeline from meddling hands? That's where we're headed next, into the razor-thin space between science and impossibility, where time travel moves from fantasy to the edge of physics. Time travel. Just saying the word sends a shiver down the spine. It's the ultimate human fantasy, the power to leap forward into the future or slip backward into the past, to witness history firsthand, to undo mistakes, to see what's coming. And here's the thing, it's not all fantasy. Physics, real hard experimentally tested physics, says that forward time travel is absolutely possible. Not just possible in theory, but something we've already achieved in small ways right here on Earth. The catch is that going backward, that's where the universe starts throwing up roadblocks. That's where the paradoxes lurk, waiting to tear logic apart. Before we start bending time, we need to understand it. In our everyday lives, time feels like a one-way street. The past is fixed, the future is unknown, and we're all moving together along the same arrow from before to after. That arrow is tied to something called entropy, the measure of disorder in a system. The second law of thermodynamics says entropy always increases over time. Eggs break, but they don't unbreak. Ice melts, but it doesn't spontaneously refreeze into the exact same shape. This gives time its direction, but relativity throws a curveball. Time isn't absolute. It's not the same for everyone, everywhere. It's woven together with space into space-time, and it can stretch, slow, and even, in some solutions to Einstein's equations, loop back on itself. Let's start with the part that's not controversial, travelling into the future. You don't need a DeLorean or a wormhole. All you need is speed, a lot of it. Einstein's special relativity tells us that the faster you move relative to someone else, the slower your clock runs compared to theirs. This is time dilation. At everyday speeds, it's imperceptible. But crank up the velocity to a significant fraction of the speed of light, and the effect becomes dramatic. Imagine you board a spaceship capable of 99.9% of light speed. You travel for what feels like 5 years to you. When you return to Earth, decades, maybe centuries have passed. You've effectively jumped into the future. This isn't just theory. We've measured it. Astronauts on the International Space Station age a tiny bit less than people on Earth because they're moving fast and experiencing slightly weaker gravity. Muons created in the upper atmosphere live longer when moving near light speed. Atomic clocks flown on jets tick more slowly than identical clocks on the ground. Scale it up, and you've got a one-way ticket to the future. The faster you go, the bigger the leap. Speed isn't the only way to travel forward in time. Gravity can do it too. General relativity tells us that the stronger the gravitational field you're in, the slower time runs for you compared to someone farther away. This is called gravitational time dilation, and it's been confirmed with experiments using ultra-precise clocks at different altitudes. Even a clock on the floor ticks more slowly than one on a shelf, because it's slightly deeper in Earth's gravitational well. Take this to the extreme. Orbit a black hole at a safe distance, and time for you could crawl compared to the rest of the universe. Spend a few hours there, and years might pass elsewhere. This is exactly what happens in Interstellar or Miller's planet near the black hole Gargantua. 1 hour on the surface equals 7 years away from it. That's not Hollywood magic. That's Einstein's math. Forward time travel is real, but it's not free. The energy required to reach near light speeds is enormous. The engineering challenges are staggering, and the trip is one way. You can't come back to the time you left. You can only return to the place you left in its future. That's the bittersweet truth. You can visit the future, but you'll never see the present you left behind again. Now we get to the dangerous part. travelling into the past. This is where physics starts to squirm. Einstein's equations don't explicitly forbid it. In fact, there are solutions, like rotating black holes, known as Kerr black holes, or hypothetical cosmic strings that allow for closed time-like curves. These are paths through spacetime that loop back on themselves, letting you return to an earlier point in your own history. But just because the math allows it doesn't mean nature does. The moment you open the door to the past, you invite paradoxes. The most famous is the grandfather paradox. You travel back in time and prevent your grandfather from meeting your grandmother. That means you're never born. But if you're never born, you can't go back to prevent the meeting. So your grandfather meets your grandmother after all, and you're born, and around it goes. It's a logical loop with no consistent resolution, unless the universe has some way of preventing it. Even if you avoid obvious paradoxes, there's the butterfly effect, the idea that tiny changes in the past can have massive, unpredictable consequences in the future. Step on the wrong insect, and you might return to a world where history unfolded completely differently. This isn't just fiction. Chaos theory shows that in complex systems, small differences in initial conditions can lead to wildly different outcomes. The past is a delicate web, and tugging on one thread can unravel the whole thing. Physicists have proposed a few ways the universe might dodge these problems. One is the Novikov self-consistency principle, which says that events on a closed time-like curve are self-consistent. You can't change the past in a way that creates a paradox. If you go back, whatever you do was always part of history. You can fulfill the past, but you can't rewrite it. Another idea is the many worlds interpretation of quantum mechanics. In this view, travelling to the past creates a new branch of the universe. You can change events there, but it won't affect the timeline you came from. You're not really changing your past, you're creating a new one. Even if paradoxes weren't an issue, the practical challenges are enormous. Creating a traversable wormhole or a warp bubble, two of the most discussed theoretical time machines, would require exotic matter with negative energy density. We've seen hints of such effects in quantum physics like the Casimir effect, but nothing close to the scale needed. And then this stability. Wormholes, if they exist, might collapse instantly without exotic matter to hold them open. Black holes might evaporate via Hawking radiation before you could use them. Cosmic strings, if they exist at all, are purely hypothetical. Stephen Hawking famously proposed the chronology protection conjecture, the idea that the laws of physics conspire to prevent backward time travel on macroscopic scales. In other words, the universe protects its timeline. Maybe quantum effects destroy any time machine the moment it could create a paradox. Maybe the energy requirements are simply impossible to meet. It's not proven, but so far nature seems to be on Hawking's side, Thetis. Despite all the problems, time travel remains irresistible. It's a staple of science fiction because it's a perfect storytelling engine. It lets us explore what if in the most literal way. But it's also a deep scientific question, because it forces us to confront the nature of time itself. Is the future already written, waiting for us to arrive? Is the past truly gone, or is it still there in some higher dimensional sense? Are we moving through time, or is time an illusion created by our consciousness moving through space-time? These aren't just philosophical musings. They're questions at the cutting edge of physics, where relativity, quantum mechanics, and cosmology collide. Here's where we stand. Forward time travel is real, tested and built into the fabric of relativity. We can do it now in small amounts, and in principle we could do it dramatically with the right technology. Backward time travel is allowed by some solutions to Einstein's equations, but it's plagued by paradoxes, stability issues, and energy requirements that may be impossible to meet. If the universe allows it at all, it may only be in ways that prevent us from rewriting history, or in ways that take us not into our past, but into a past that belongs to an entirely different branch of reality.